Hey guys, today's topic is going to be SMD, and by that I don't mean surface mount device, I mean silver mica disease. What is it? What to look for? What to do about it? Why you should even care? Is it even going to be a concern for the type of device you work on? Let's find out. I wasn't really planning on doing a video on silver mica disease because it's a topic that's been covered many times in forums, magazine articles, and probably other YouTube videos. But two reasons brought me to make this video. One is this radio, which is a classic Zenith Model Y832. It's an AM/FM radio from I think the late 50s. It has electrostatic tweeters, big mid-range speaker. It's supposed to be a very well-performing radio. They made this chassis in a lot of different cabinet styles, I believe. They made it for a number of years because it really worked well. However, my buddy and I recapped this radio and we were a little disappointed because strange things would happen with it. The gain wasn't so great at times. By that I mean it would kind of sound good for a while, then maybe be some crackles, and then the volume would drop off a lot. Or we wouldn't hear anything on parts of the band. Just a lot of like strange, kind of like gremlin problems. And so we got to talking and thought, well, you know, it's a pain to deal with, but this radio just might have SMD. So we investigated, and sure enough, it does. The other reason I'm making this video is somebody asked a question. A number of people have asked this question over the years, which is, why is it a problem in radios but not TVs? And I gave a short answer, but in hindsight, I thought it deserved more than that. So we're going to talk about that as well. First up though, what is SMD, silver mica disease? Well, unfortunately, in some radios for inside the IF cans, they used mica capacitors, which are super stable with temperature and value, some of the best caps made, but they're not encapsulated. They're not protected from the environment. They are exposed to the environment. And just as the name says, silver mica. This is a sheet of mica with silver deposited on both sides. Conductive surface, insulator, conductive surface, you've got yourself a capacitor. Cool. And if we look close, well, you can see on this side we have three pads. One, two, and then a larger one up here. On the flip side, we've got a section here and then one isolated there. So what does all that mean? It means this cap is completely isolated on its own because both pads are separate. These two caps share a common section. Okay, cool. If you look on the schematic for this, it makes sense. That's three capacitors and two of them have one and connected together. But take a closer look. Now it sure isn't gleaming silver now, is it? Well, that's because it's been exposed to air and silver tarnishes. You get silver oxide. So it starts to turn gray and then black. However, there's a little bit more to it with these capacitors, unfortunately. And that is, probably a little hard to see, but if you check out the edge of the black, like around the top here, it's creeping towards the edge of the mica. When this was originally made, there was probably a 1/16 of an inch all around that was just bare mica. What happens is, kind of like with tin whiskers, which is a somewhat related problem, if there's enough DC bias applied across it, the silver ions start migrating, and eventually they will short out. So I've heard that the problem has a number of factors. One, construction, and two, how much voltage is applied across it. The higher the DC potential, the more likely it is and the more quickly this problem develops. It's a little bit of inexact science. So I mentioned a moment ago, like, should you be concerned about it? Maybe. There are certainly people that have this model radio and it doesn't have that problem. It could be the environment it was stored in. It could be it wasn't operated as much as other other examples. Like, in other words, maybe it's a low-hour set, or some other factors, humidity. It's a little hard to say exactly why it happens or when it will happen. But it certainly is a problem in radios that have exposed mica. Now, not all radios used this type of construction. It just so happens I like the styling of earlier radios, particularly from the 30s, kind of the golden age of radio. Those don't have this problem because they didn't make the caps quite like this. The IF cans had different types of capacitors, usually ceramic, and there'd be screw adjustments on the top that you'd tighten down. Now, they were mica and they were silvered, but something to do with the construction, maybe the conductive material had more of a gap from the edge. Or actually, now that I think about it, I don't think they've deposited the silver on the mica. I think it was literally like a sheet of metal, and then a sheet of mica, and then a sheet of metal. I think it's really an issue when it's like vacuum deposited, or however they did it on this. Because I think that means there's a higher tendency for the silver to migrate when it's deposited like this, rather than being like a solid piece of silver. Okay, so what does that do to the radio? Well, if we were to take an ohm meter and put it on one side and put it on the other, the resistance should be infinite in an ideal capacitor. And on this, I can tell you it's not. It's several mega ohms. So it's not like a dead short, but there's some connectivity, and there shouldn't be any. So what will that happen? What will that do to the radio? Well, it depends. If it's on the oscillator coil, it's going to throw off the tuning frequency. If it's on the IF, well, a couple things. One, if it's a really good short, meaning it's say 1 mega ohm, it's going to form a leaky capacitor. It's going to throw the peak of the IF off, and it's going to decrease gain. What's more common, though, is that it's kind of a partial connection, like maybe just a few atoms, a few mega ohms of resistance, and the DC bias will blow it open. And then the atoms will creep together again, and it blows it open. Creep together again, blows it open. So you end up getting a crashing, a hissing, a crackling sound. And if it takes a bit longer to reform between breaking apart, like I think we experienced with some of the coils in this, it would sound good for a while. Maybe 5-10 minutes, maybe a few hours, and then it craps out. Unfortunately, the reason we eliminated every other possibility first, like we checked all the tubes, we double checked their work and all that, is that there are a lot of cans in this radio. Altogether, I think we've got 1, 2, 3, 4, 5, 6. We have 7 cans that we are going to have to take apart and fix. That stinks. Now, we don't know that they're all bad, but reading about this radio, plenty of other people have had the same problem and even posted photos that looked exactly like this. Now, the schematic for this radio does not show the value, but luckily enough people have dealt with this model that they've reverse engineered the value. So how do you do that? Well, just because a capacitor is a little bit leaky, like maybe say it's 5 or 10 mega ohms, the higher the resistance, the better. You can still measure the capacitance. If it's like a dead short or like only a few hundred ohms of resistance, you probably won't be able to. If you really want to go crazy, you could try to measure the surface area and the thickness of the mica and all that and figure it out mathematically, but that's not realistic. If you can't do either, if you can't measure it and you've got nothing else to go on, Ballpark for 455 kilohertz IF radio, so we're talking about an IF transformer, somewhere between 1 and 200 picofarads, probably. This radio is a little bit more complex because like this has 3 caps and 2 of them share a common section, but most of them in this are, I think, 120 picofarad or thereabouts. I think several are 180 and maybe there's one that's 100, something like that. But I think the vast majority, all but like 2 or 3, were about at 120. So, and that's a pretty common value. So that's one good thing. But I'm getting ahead of the game a little bit. So, as far as what do you do about it? What do you do about it? Well, you got 2 basic options: repair this or replace it. You can get modern mica caps. They look something like this. They're usually dark brown, sometimes they're yellow. They're not used that much anymore. Things are going surface mount device or ceramic. So don't be surprised to pay $2 or $3 each. So in a radio like this, we probably need at least a dozen. So we're talking $25, $30 in mica caps. So then you gotta think, well, is a radio worth it? But there is another option, which is to get out a pencil and use the eraser and literally erase around the outer edge and erase the corrosion away. I read about one guy in the antique radio forum who did it, put him back on the radio, and he said it's been working fine for a while, but that's what I said, like, it depends. Will it come back? Probably. I mean, it happened once, why wouldn't it happen again? How long will it take? Who knows? I've never actually done this before, but yeah, I can see it's getting shinier there and the black crud is going away. So I imagine you want to work all around the outer edge until all the black is gone and then put it all back together. That is a pain, especially with this, because the construction on this thing is, it's the worst one I've seen of any IF I've taken apart. So here's the bottom of the IF can. There are, I think, 5 or 6 legs on it. So here's one of the legs. The other end of the leg is a pad that presses up against that mica cap. There's nothing holding this in place except pressure of the whole assembly put together. So you've got this, and then you've got the other legs here, which are going to very fine wires going to the coil. And this sits kind of in a sandwich between the legs. I think some go on top, some go below, something like that. And then you've got this, and there's a screw that runs through it, and a nut, and a washer. It's a sandwich, in other words. So that's kind of a hassle. Well, what you can do is throw this away. Put it all back together and use external caps. Now you will have to modify some of these pins so that they don't short into each other, because you can imagine there's a pad on top on one side and there's a pad on the other, and the mic is supposed to be in between. You take the mic away, those 2 pads are going to short into each other, so you have to clip these off. So, and then do that for 6 other IF transformers. Not much fun. So what radios used IF transformers like this? Well, this is one of the earlier types I've seen that has this problem, and I think this radio is from like 56, 57, 58, somewhere in there. And for sure, when you get into the 60s, a lot of them do it. Your classic All-American 5 with the smaller kind of plastic IF transformers are very likely to have it. On those, it is a mica cap in the base. That's where I think where they always are. And those, instead of having a screw and a nut and a washer, are sort of riveted together. They're pressed and kind of held with pressure of a metal ring that's smushed down. I've never had to, or maybe I did repair one of those years ago on an Admiral radio that used a PC board, as memory serves. Basically, I noticed you have to drill out that kind of rivet and then chip away, get out the mica, put it back together, and then use external capacitors. So assuming you're going to go the external capacitor route, you get it all back together, make sure nothing's shorted, and then you just attach your external caps on the bottom. In this case, we need 3 of them. That's simple enough. So primarily All-American 5s. In this case, this has, it's an AM FM radio. It's got more like 8 tubes in it, but your typical series strung set from the 50s and newer. It's quite likely to have this problem. Radio from the 20s, 30s, early 40s, very unlikely to be an issue. Did that pencil eraser make any difference? Let's find out. I've got my multimeter here set for ohms. Let's check each one of these sections again. You got to be careful. I don't want to break through the wafer. The probe on either side should be infinite. Looks like this section is. Let's check this section. So looks to be infinite. And finally this one. Kind of hard to do all this without crushing the wafer and getting your fingers on there because they will affect the reading. There we go. So yeah, it looks like this did. Sorry, I didn't show you a reading beforehand, but I can simulate that with my finger. It was something like that. It was in the mega ohm range, and then after the eraser, it is now infinite. Would I recommend doing this, especially since there's still a lot of black crud on there? No, because I think this will develop a short again at some point. Impossible to say exactly when, but at some point I do expect the problem to reoccur because we didn't solve the problem, we just did a quick fix. Well, let's look at some other types. So I mentioned about earlier caps not having that issue. I couldn't find a spare IF can readily without pulling one out of a radio, but this is the general idea of how the earlier adjustable caps are. Where yes, there is some mica, and there is metal on either side, and there is a screw that provides tension. The tighter you make that screw, the more capacitance you have because it pushes the metal closer together. However, notice this is not like vacuum deposited very thin layer of silver. It's an actual piece of metal, and I don't think it's solid silver. It might be tin or I suppose even steel. Something that doesn't corrode. The rest of the chassis you can see is very yellow. This is cadmium plated steel. But I think this is something different. But I don't think it's tin, because tin can also develop problems where it can develop tendrils. Similar idea when there's a voltage potential across it. The tin atoms will start forming, well, thin like fibers that can eventually short out. It's a problem with a lot of controls on early sets. But yeah, generally these don't have any problem. And they use, so this is a trimmer. A trimmer's on a variable tuning capacitor, but they also use the same technique. And the IF cans for transformers from the 30s for sure. Into the 20s, things get a little weird because it was sort of early days with the radio, and there were a number of different ways to do it. But for sure, the 30s, this was the standard way to do it. And into the 40s. Again, the silver mica disease seems to really be an issue. You get into the 50s and 60s for sure. I pulled out some other types of cans. I'm not exactly sure what this one's from. I just went through my junk box, and let's see what's going on in this one. I'll also give you some idea how to take these apart. So in this type, unlike the Zenith, which has a threaded screw and nut on the end, this is a fairly common 40s type where there's a phenolic insulated shaft running up through the middle, which would have the coils around it, as we'll see. And then the top has sort of this collar with flanges that can, you push them through the hole, they spring apart.
Hello, Moto.
Interruption there. So to get these apart, you simply can push these together and then carefully push it. Sometimes you do it with just your fingers or use a pair of pliers, and then the whole thing just slides right out. And then typically the can itself would be going through a couple holes in the chassis and then a couple nuts down below. So to really take one of these out, it's unfortunate, but you have to undo all the connections, undo the nuts, and pull it out from the top, squeeze the flanges together, get the shield off, and then you can finally get at the insides. And in this particular type, which you do encounter, there do not appear to be any capacitors. This might be an oscillator coil, or it might be a type of IF where they had the capacitors mounted externally. You don't see that too often, but it's not unheard of. Early 30 radios, I think I've seen that in some Filcos where all the IF capacitors, mica caps in the range of like 47 to 150 picofarad, are external to the cans, which may very well be the case for this coil, which is a good thing. I mean, you know, there's absolutely no reason to have to do anything with this unless maybe occasionally. Another problem with these is at the end of this threaded shaft there will be a piece of compressed powdered iron core, most likely. And as you turn this, and boy, they really made it easy to adjust on this, where there's actually a knurled nut on the end. More commonly, there's a split in the shaft, and you have to use something like an insulated adjustment tool, or in a pinch, a flat-bladed screwdriver and turn it. But this one, boy, they really made it easy. So this is moving that iron core up and down, which affects the inductance of this, but also the coupling between these two coils. And sometimes there's one at the bottom, and this one does have that split shaft like I was talking about. So there'd be two cores in this, two separate shafts. This shaft does not go all the way through. There is one at either end. And when you do the alignment, you need to adjust both. And you'll usually have some instructions like put them both all the way out and then start bringing them both towards the middle. There'll be some sort of rhyme or reason to it, otherwise you can drive yourself nuts about moving them in and out and so on. So this could be an FM coil for a ratio detector, or this could be an IF coupling coil. I don't know where this came from, but there's the part number if somebody wants to look it up. 20C12572-1. Might be a Zenith part number. I'm not sure. Okay, now so those are radio, I'm pretty sure. Let's take a look at some from TV. So these are from an Admiral TV. Similar deal, where there would have been there'd be a hole cut out in the chassis for all these lugs to come down through, and then two holes drilled for nuts to mount it down. And the top of this one, now this one looks like it is secured at the bottom. Well, as is this. So these early type Admirals, I guess they didn't. The later type Admirals for sure have that split metal collar on top where they spread apart and snap in. Now to get these out, it's actually pretty easy. Once it's out of the chassis, you just undo these nuts. And then the entire thing slides out. Now, a weird thing about some of these early TVs is there may not be any caps inside, but sometimes there are some power resistors, which seems like an odd thing at first, but remember, for TV IF, you want a wide bandwidth, like on the order of 4 megahertz. Whereas on an AM radio, you want a pretty sharp peak. On FM radio, you want something like 30 kilocycles wide, or whatever the FM bandwidth is for stereo. Let's see if this comes out now. Huh. So maybe just with age it's widened a little bit on top. Those are really early type. Probably from their first generation TV chassis. Maybe just a little whack is in order. There we go. Ah, excellent. This is exactly what I wanted to show you guys. I had no idea what this exactly was going to find in here. So this is interesting. So let's take a look at this. So there's a few types of coils, transformers you'd find in a TV or radio. Some are going to be for the local oscillator that would be in parallel with these tuning caps, and that would set the local oscillator or bandpass filter on the antenna, that type of thing. You're going to have IF transformers that couple the signal between stages and provide a filtering action, typically 455 kilocycles for radio. For TV, early TVs 21 or 22 megahertz, later TVs and up until modern era 44 megahertz. Some other coils you'd find would have a trap on them. So that's what this is. So there are two coils on here. One of them has two wires going to the bottom, and it looks like a parallel capacitor. Now this is something you'd commonly see in TVs. They don't have those silvered mica caps, typically in the IF. They'd have these ceramic tubular caps, which you get in very small values, sub-picofarad values even. Extremely stable, virtually never go bad. What's the difference? Well, instead of a piece of mica, it's a ceramic tube that they vacuum deposit metal on. The inside and the outside, and they wrap a lead around each end and then coat it with some paint with color coating on it. Virtually indestructible. And they also threw a resistor in here. Those can drift off values, so occasionally you may need to open one of these up. Why do they stick it in there? I think basically because they could, so that they could drop this in as a complete assembly. All right, so we've got one coil, and then there's another one wrapped around it with this thing here and no wires going down. So what is this? It's not a coupling transformer. What this outer one is, that's a trap. This is a capacitor. This is an exposed mica cap. This could go bad. So it is possible in TVs, early TVs typically, I'm talking like 46, 47, 48, would have traps in them. Later TVs, you generally don't see that. So, but it's not going to anything. So what the heck does this do? Well, it's an LC tank. It's a coil and a cap in parallel. This will form a trap. So whatever the resonant frequency of this is, if a signal came in, this would basically absorb it. It would, because at a resonant frequency, this is going to have the least resistance, which is going to act like a dead short to that frequency. The further away from you get from that frequency, the higher the, I should say, impedance of this would be. Reactance, I guess is another way to, maybe the more appropriate way to say it. Why would you do that? Well, a typical common reason you do it is you don't want sound leaking into the video. So when a TV signal is AM modulation for video, FM modulation for sound, and the sound is 4.5 megahertz above the video carrier. So you might very well have a trap at 4.5 megahertz in the video IF chain, for example. But what about the rest of this? This could very well be a pickoff coil. So it gets complicated with TV IF in the early days because they needed wide bandwidth, and there's a bunch of ways to do it. Some early sets used They would dampen out the IF transformers by putting a resistor in parallel with the coil. Others use stagger tune, so they might have 3 IF stages that each be tuned to a slightly different frequency to spread out the response. Another way to do it is to kind of have series peak transformers and like RC couple the stages. So you might say your IF frequency is 21 megahertz and you want it to have a wide bandwidth. When I say 21, it's kind of, your bandwidth is like 4.5 megahertz, so it'd be like 21 to 25, let's say. So you might have 3 peaked amplifier stages, like one at 22 megahertz, one at 23.5, and one at 25, something like that. So you'd kind of like, and if you add the sum of each of those peak stages together, you'd get not a perfect flat response, but something approaching it. So that might be what this is. It might be a peaking coil with a trap on it. All right. If I haven't confused you enough already, the whole point of this is, generally speaking, TV transformers don't have exposed capacitors that are prone to silver mica disease in the base for the IF transformers. But doesn't mean you'll never see one. They might have one for a trap, and sometimes the audio transformers have it because the audio, the FM audio carrier is at 4.5 megahertz. So it's not as low as 455 kilohertz for an AM radio. It's not as high as 20 or 40 megahertz for video IF, but 4.5 is kind of in the middle. So I have seen some of those where there'll be a mica cap that's maybe 20 to 30 picofarad exposed just like this. And I have had to replace some of those. So that's why I was saying the answer to his question about why don't TVs have the same problem, sometimes they do. Generally they don't, but sometimes they do. But typically they don't on the IF, but they might on a trap, they might on the FM transformers. I don't know what this one is either, but let's see. And sometimes, okay, what's in this guy? Same deal, huh? Well, this one you can clearly see there's a 90 on there, so that would be 90 picofarad. Huh, and this one I clearly worked on because that is a type of resistor I used to use a long time ago. So this must have been from a set that I was working on and then abandoned for some reason. Huh. I could look up this part number. Maybe I will. Boy, that's a heavy shield on that, man. This is this stamped aluminum, but that might be tin-plated steel. So it is a 72A81. Now the first generation Admiral design, the 30A, 30B series, are pretty similar in a lot of ways to the first RCA 10-inch set, the RCA 630TS, and that used a bunch of traps in the IF. So I suspect that's where these came from. The later sets do not. So again, yes, I should not have been so short with my answer saying the TV transformers don't have silver mica disease. Yes, they can. I went hunting around and dug up a couple more IF cans. At least I think that's what they are. So let's see what's in these. Now here's another type of construction. Again, aluminum shield with threaded shafts. Go through the chassis. Super cheap pressed metal nuts. But can't get the can apart. It also has the top collar, but you can pinch that and it's not going anywhere. Why? Because they also pinched in the bottom of the cans. To undo those, I have this snub-nosed pair of pliers here that works pretty well. I mean, you're going to have to deform the metal. There's not much way around that. And then do the same. You put it back together and hope that the metal doesn't snap from metal fatigue. Let's see, I think it's pretty filthy on top. It's a little hard to see what's going on. There we go. Now this is typical of a 40s TV IF transformer. No capacitors to be seen. They're not hidden in the base, nothing to worry about. You make adjustment from the top, probably only the top. Sometimes there's one on the bottom too, through that hollow opening. But often it's not, it's just a single core and you'd be moving it up and down to adjust the coupling between them. And if there are caps, they are external, like those tubular ceramic types. So what I suggest, if you're working on TV and you get a weak gain, you think the alignment might be off, check the schematic, see if they show capacitors in parallel with the IF transformer coils. Look underneath the chassis. If you see capacitors mounted around the base of the transformer, you know that there aren't any inside. If you don't see any, and you've eliminated every other possibility, then yeah, you might have to go hunting inside. You know, if you look in the TV forums, you don't hear about it much because it just doesn't. Most don't have them, and even when they do, they're typically the internal ones are the ceramic types. And even the exposed mica ones don't seem to go bad as often as their radio counterpart. Now this, I just grabbed out of a parts bin. I think this might be for a radio. But notice this has ceramic caps inside. So, wasted effort here. There would not be any issue with mica. Ceramic caps virtually never go bad. What they do though, and the reason they didn't use them back then much, is they drift with temperature unless you get a very specific type of NP0 or C0G ceramic, which these are not. I mean, N75, that is the type of dielectric, and it has a temperature coefficient. It drifts with temperature. Not sure about this one. 68 is probably the value, whereas I think that's 50 picofarad. Not sure what type of ceramic that is. Not the same deal. Or maybe the ceramic type is 68N and the value is 220. Not entirely sure. So how could they have capacitors in here that drift with temperature? Was the radio went through different temperature site ranges? Wouldn't the tuning shift? Yeah, it would. Depending on the type of ceramic. Some of them, when you're just around the room temperature range, it might not drift that much. Or they may have other components elsewhere that drift in the opposite way to compensate for this drifting. Because some components will, like say, increase with capacitance with temperature, some may decrease. So it is possible to balance them out. Sounds like an engineering headache, but it is possible. How about we take a look around and see if we can find some more radio chassis and look at the type of cans they have and see if they might have silver mica disease or not. So this is a Motorola from the late 40s. One I'm fairly fond of. Haven't restored it yet, but unfortunately it had rodent damage, so it kind of turned me off working on it, but someday I'd like to get to it. Regardless, let's take a look at the IF cans. What have they got in the top? They do not have a threaded shaft sticking out that you would put an alignment tool on. they've got holes. Now, it's hard to see, but if you were to peer down those holes, you would see the two larger holes, that is, on either side. They have like flathead screw heads in them. Those are adjustable capacitors. These are the type that do not get silver mica disease. Two pieces of metal with an insulator in between, you tighten down that screw and it changes the capacitance with fixed inductors. So that type, very unlikely you would have any issues with those caps. Now let's take a look at a classic Filco tombstone radio from the mid-30s. It's a Model 623 farm radio, meaning it runs off of a DC battery supply. Here are the IF cans, and just like the Motorola, there is no adjustable inductor core. Instead, we've got flat-headed screws. This has adjustable capacitors, fixed inductor. Very, very unlikely to have any problem with these. And that's what you're going to see. Radios from the 30s don't generally have silver mica disease. Sticking with Filco, let's go a little bit further back in time. This is a Filco Model 90 from the early 30s. Here are the IF cans. Now, wait a minute. There are no holes at all in the tops of these. What gives? Well, there are some largish holes in the chassis. And down in there, there is an adjustment you can make for these guys. That and that, those are adjustable capacitors. Couple metal plates, insulator in between. I do believe that is mica. So why don't these have an issue? Well, it's because it is not silver plated mica. It's two pieces of metal, probably cadmium plated steel or something like that, with mica in between. There's no silver to migrate, so it's not a concern. And inside those cans, it's just inductors, just coils of wire around a form. There are no capacitors at all inside these cans. Here's something a little different. It's an FM only Emerson radio from, I believe, the early 50s, maybe late 40s. Inside, notice things are a lot smaller. It's all miniature tubes, small IF cans, and just a single hole in the top. Well, that is for an adjustable core. Variable inductor, fixed capacitors are probably in the base, probably mica. This is a candidate for having silver mica disease. Now, you may have sensed the pattern here. It's from the 20s or 30s, very unlikely to have it. Mid-late 40s, maybe. 50s and onwards, quite possibly. I don't mean to discourage you from working on newer radios. They have features like FM sound, and generally, if it's a well-designed set, they have better gain and selectivity and, well, generally sound better. But things are smaller, harder to work on, and they might have silver mica disease. Gears a little bit and look at some service info to see if we can find some clues as to whether or not the TV or radio has any mica caps inside of the IF cans. So for example, this is the very detailed factory service data for the early Admiral TVs. That's where those first two cans I showed you came from. Now this is almost 75 pages of detailed info with theory of operation, a very detailed parts list. There may be some clues in that, but I want to jump right to the schematic. And let's look in particular at the IF. So here we have 3 IF cans. And the thing up top, that is the trap we were looking at. There's the 90 picofarad mica cap we saw. There's the resistor, and there's the coil. If you look at the theory of operation, they tell you how it works. It's like self-resonant in this part, I believe they call it. And then these are traps. And the reason they chose these frequency traps, that's a trap for sound, and these 27.25, 19.75, those are traps for the adjacent station to the one that you're tuned to. So you want to get a band pass for, say you're on channel 5. You want to block out channels 4 and 6, so you want really sharp cutoffs on either side of that. That's what these traps are for. Okay, so anyways, from looking at this, if we see the dashed line, that represents the IF can. And if we see a capacitor inside and labeled ideally with a value, yeah, there's a pretty good possibility that there's a mica cap inside. Could be ceramic. You won't know for sure unless they tell you in the parts list. Or another possibility is if you look up the part number, you might be able to find a data sheet for it that shows you what components are inside. That's kind of a stretch, but it is possible. So definitely if I saw these and I was having any issues with the IF and I eliminated the tubes and checked any paper caps and so on, I would want to take a look inside of that can and check out that 90 picofarad cap. If we go up and look at the sound, similar deal. There's a sound IF transformer, and this is a more conventional IF transformer where you've got a primary and a secondary, and it's a tuned secondary, 30 picofarad fixed cap, and a movable slug. And I know from experience, because I've opened these up, that is a mica cap that gets silver mica disease, and so is that. Now let's take a quick look at the next generation of Admiral TV chassis that came out a year or two later. The 20 series. This is the SAMs, a little bit different layout than the Riders, but all we care about is the schematic. And here is the IF. And notice right away it looks a little bit different. There are no traps. And this has a primary and a secondary. And there are no capacitors. And this is typical of a more modern TV. This is when I was asked, hey, how come TVs don't get Mica disease? I was thinking of newer TVs. They don't have them. It's just 2 coils of wire with a movable slug. So if I was to look at the schematic for this, if I had trouble with the IF, I would very quickly conclude there are no caps inside those cans. There's nothing to check. I need to check all these external components, check the tubes, check the voltages, and so on. Now let's take a look at a radio. This is an early type All-American 5, one that uses octal tubes, probably early 50s I would guesstimate. So here are the 5 tubes, and if we look, here are the IF transformers, and what do we see? Capacitor symbols inside the dashed line. So these are very likely mica caps. And notice there are no values. Unfortunately, that is typical of All-American 5 designs. Just like that Zenith I showed you at the start of this video. Those are not labeled on the schematic. Neither are these. So, trial and error, you can figure it out. Start maybe at 120 picofarad. They're typically in the range of 100 to 200 picofarad for a 455 kilohertz IF. Or if you can, like with that Zenith, once I removed the partial short with an eraser, I could use a capacitance bridge and measure them And luckily other folks have online, and I was able to find all the values. I initially did that I found the part number of the IF can. I did a Google search on it. I quickly found other folks that had restored that same radio with the same problem and had done the hard work that I got to benefit from because they stated what their values are. But often you're going to have to do a little trial and error. Another thing you can do, you can remove these and put a variable external ceramic type variable cap, maybe like 750 to 300, something like that. And once you find the value that seems to work right, you could replace that variable cap with a fixed capacitor, which costs less, take up less space and whatnot. Now here's another radio. This is a Filco 46420. It's sort of an all-American 5. Actually, I think it has 6 tubes from 1946, using a mix of loctal tubes and octal tubes. The key point here is inside of the IF cans, what do we see? It looks a little bit different. Dashed lines, primary, secondary, but notice there's a little arrow through the caps, variable caps. And notice there are no lines here indicating an iron core. This is typical of earlier radios, where instead of having a movable slug with fixed capacitors, they had variable capacitors. There'll usually be a couple holes in the top of the can for a slotted alignment tool. You put it down in there and you tweak the capacitance values. These won't have silver mica disease. Might be a little bit of debris that's fallen inside the can because they have those open holes and typically a lot of dirt and whatnot falls in there. But I don't think I've ever had an issue with them where I've had to open one up. And again, over here. So basically, if you're on the schematic, you see dashed lines, you see a variable core, you see a fixed capacitor or two, quite possibly silver mica. If you're lucky, they're ceramic. If you're not, they're exposed mica that may very well have a problem. If you see that they're variable, or of course you don't see a symbol at all, I would check everything else first. And there probably are not any capacitors inside that can that needs to be fixed. I would have liked to have shown you some examples of the type of IF cans where the mica caps are riveted in the base. Just don't have any on hand right now. However, I do know there are a lot of videos on YouTube showing what they look like and how to replace them. I know Shango's done a bunch. I will try to include some links in the description. That's going to be it for now. I hope you gained some insight. I wish you luck. I hope you never encounter this problem, but if you do, good luck in repairing it. It's worth the effort. The radio will sound and perform much, much better if you take the time and effort to tackle this problem.